Swayam Prabha. Digital India. Educated India.
So my own work is in the area of quantum dynamics and quantum computing. So the idea is that can we use quantum computers to do quantum dynamics hopefully someday in large enough systems. So I will show you two methods that we have developed for quantum dynamics. One, we call that analog quantum computing, where Hamiltonians for wavepacket dynamics are mapped directly onto quantum systems. And secondly, we also have a digital paradigm where we try to bring down the quantum circuit depth by several orders of magnitude, and I'll talk to you about that. And we also have new methods for doing electronic structure theory on a quantum computer. So, of course, we all like money a lot, right? I mean, money is the most important thing in life, right? Yeah. I mean, we should, and in fact, why are we doing quantum computing? It's because of money, right? Peter Shor's algorithm is for prime factoring, which is actually the way in which information is transmitted on the internet, including financial transactions. So the entire reason why quantum computing is so interesting today is because if we do get a quantum computer, the entire stock market will collapse. So it's not chemistry, it's not physics, it's all money, right? Okay. So how does prime factoring work on a quantum computer? So you have a quantum system which is represented using a set of qubits here on the left. And for us as chemists, we could actually think about this set of qubits as a bath variable and this set of qubits as a system variable. So it's a system bath simultaneous quantum dynamics. Of course, there's prime factoring going on here. And the bath is initially prepared in a state where all components of the bath are ready to receive information. And the kind of operation that occurs is called a Hadamard transform. Once that is there, at this particular red slice, the bath is ready to view everything that goes on in the system. And there is a unitary operation that is specially prepared in the case of Shor. It actually obeys Fermat's Rittel theorem, and following which you do a measurement on the system and a Fourier transform on the bath. Okay? And once you do the Fourier transform on the bath, the spectroscopic peaks, as we would call it as chemists, give you the prime factors of an integer that is encoded in this particular quantum system. This is how prime factoring works, and Shor's algorithm is the basis of Shor's algorithm. But you can see that the way in which I've described it to you as a quantum dynamicist, right? So you can think about this system baths problem that is evolving in time. There's a concerted unitary evolution operator that's acting on the entire system, and you do a Fourier transform on the system. That's what every spectroscopist would do, and that gives you a spectral feature for the system. This, of course, is Shor's algorithm, but this also is the basis of all quantum algorithms, which belong to a class of mathematical problems called the hidden subgroup problems, which turns out to be very hard problems in mathematics. And the basis for quantum computing is that these hard mathematics problems can be solved on a system that obeys quantum mechanics. And hence, we have this postulate back in the 80s and the 90s that if you develop a quantum computer, you might be able to solve all of these hard problems, which all come from the Simon, Deutsch, Josta, Vazirandi-Bernstein family of algorithms. And they all have exactly the same mathematical structure as laid out here. So, talk about number theory, we talk about hard mathematical problems, but then we also think about things like spectroscopy here, okay? So if you have a chemistry problem, a wavepacket dynamics problem, and you do a spectroscopy, the mathematical similarity is there for us to see. Okay. So then, of course, the question to ask is, will we someday be able to study quantum dynamics or electronic structure on such a quantum system? Will that ever happen? We'll be able to factorize very large numbers. To me now, those two are similar questions because of the previous slide, right? They're mathematically related. One of the big problems that we have in quantum computing is something called the quantum circuit depth. So I showed you that there's a unitary in the previous slide that evolves forward in time, and that unitary is performed based on a set of gates, all right? These are quantum gates that are concatenated one after the other. And these quantum gates are actually experimental techniques that are used to propagate these small quantum systems forward in time that are part of a big quantum system. And so, as of a couple of years ago, the entangled gates, one of which is called the C0 gate, had a fidelity of 95%, which means 95% of the time if you interrogate it, you get the correct answer, 5% you get the wrong answer. The problem that happens is that when you have gate depths of the order of 10 to the power of 10 with 95% fidelity, you essentially end up with completely wrong results, right? And that's the problem. The reason why we cannot do quantum computing today is because most problems in quantum computing, and here I've got a very simple problem with just H2 clusters. There are 64 of them, and the basis is STO3G. So it's electronic structure, okay? I'm using VQE, and the circuit depth goes up exponentially. So it's a very hard problem to do. What I'll show you in this particular talk is that we have developed methods both for quantum nuclear dynamics, wave packet dynamics, as well as for electronic structure that brings the circuit depth down by several orders of magnitude. So there are two families of methods that we have. One, as I said, is the analog quantum computing method, right? And that's right here. So what we do is that we take some generic Hamiltonian for a nuclear wave packet dynamics problem, and we map it to what looks like an Ising model. Okay? Now this Ising model is something that can be implemented on ion trap quantum computers. So this is a theoretical result where we show an exact one-to-one correspondence between the terms of this Hamiltonian and the terms of this Hamiltonian in such a way that when you do the dynamics of this Ising lattice, all right, you get exactly the same dynamics as, in this case, the hydrogen bonded system that I'm going to talk to you about. Then we go on and implement this particular theoretical result, okay, on a real quantum computer. That quantum computer belongs to the Department of Energy, okay, in the US, and we get very high accuracy for this particular wave packet dynamics. But that's only a 1D quantum wave packet dynamics problem. It also turns out to be very hard, though, on a quantum computer. Then we go on and ask, is it possible to ever do multidimensional quantum dynamics? And we develop a method that is called tensor network based quantum dynamics, where an individual wave function in multiple dimensions, here is shown in 2 dimensions, is entangled through this internal variable, and then that gives you several copies of quantum dynamics trajectories, which are wave packet dynamics trajectories, which are all individually propagated on multiple quantum computers. So we implement this on IonQ's 11-qubit harmony quantum computer, and we did this last year, and we show that that works too. So that's in quantum dynamics. Electronic structure, we have come up with a graph theory based fragmentation of quantum circuits. Okay, so it's very similar to the fragmentation approaches pioneered by Professor Gadre and Professor Raghvachari. Okay, and so it's very similar to that, but then we apply it to quantum circuits, and then we end up with a family of quantum circuits that are all solved in many different quantum computers. We implemented that on IBM's quantum systems, and we get pretty good accuracy on that one too. And more recently, we have used the same idea to do machine learning for large systems. This has led to the first 186-dimensional potential surface done using coupled cluster accuracy using machine learning. So with respect to analog quantum computing, so this is a collaboration between my group and so Phil Risherm is an atomic physicist at Indiana University. So he builds quantum computers. He builds ion trap quantum computers. And Amar Sabri is a theoretical computer scientist who basically works on new compilers for quantum computing. So we have come up with this approach where we actually take a wavepacket dynamics problem and then map it to an ion trap problem. So essentially, you can see that what the goal of this problem is to now take the various components of the nuclear wavepacket dynamics Hamiltonian. Okay, so it's got the kinetic energy term, it's got the potential energy surface. These are now mapped onto the individual B and J terms that exist in an Ising model that operates an ion trap. So these sigmas are the polyspin matrices. The polyspin matrices are acting on the individual qubits of each ion, and the B and the J values are the individual coupling elements between these individual qubits, and those coupling elements are now derived from the potential and kinetic energy terms. And these expressions were derived by my graduate student Debajita Saha, who's now graduated. She has become a postdoc at Princeton working on quantum biology. And what these expressions show you, on the left side, you've got the kinetic energy terms, the potential energy terms of a molecular Hamiltonian. On the right side, you've got the individual terms that come about from the Ising Hamiltonian. And using the Hamiltonian for the molecular system, she works out the various values of the Ising Hamiltonian. So then you can now propagate the ion trap system, and the ion trap system is now doing exactly the same quantum dynamics as the molecular system. This is the idea. The way in which she comes up with this map is by taking the Ising lattice Hamiltonian and writing it in the total angular momentum space. And these are the different slices that you get for different angular momenta. And she shows that if you can characterize these separately into different blocks, that gives you a structure for the Ising lattice. And that structure is then used to connect the two Hamiltonians. So this is the nuclear Hamiltonian, this is the Ising Hamiltonian, and this structure now can be connected using a transform, a Givens transform. And once she gets up the Givens transform, she can work out these equations, and these equations now allow you to compute the B and the J terms, that are the characteristic terms that operate the ion trap. And once that is done, we can look at the dynamics of a simple hydrogen boron system. That's what we have. It's a double well here, potential here, and I've got this double well potential on 8 grid points. Okay, simple. So 8 grid points is 3 qubits. So 3 qubits, and so you're doing quantum dynamics on 3 qubits in 1 dimension. So you should have 8 traces here, and the 8 traces have got 2 different, if you can see this, there are 2 different plots that are overlaid one on top of the other. One is actually the classical calculation of the Hamiltonian dynamics for the wave packet, and the other is the dynamics of this ion trap, and they match exactly. They match exactly for any length of time. So the previous simulation was short, and there's a long simulation. They give you exactly the same result. That's a theoretical result. When you go ahead and implement this on a real quantum computer, the result is a lot more noisy, but as you can see, it is good for long-term dynamics. It goes on for 10 picoseconds, right? Okay. So you can do this for all kinds of wave packets. So these are now real experiments done on ion traps. Okay, so wave packets oscillating back and forth on the ion trap. Okay, and using this, you can get a Fourier transform and get a spectrum, and the spectrum is good to 3 wave numbers accuracy. Okay, so we've now done wave packet dynamics on an ion trap, Fourier transform of the wave packet dynamics, and you get a spectrum out of that, and it's pretty good. But this is only a 1D system. It's only a 1D system. What happens when you go to higher dimensions? Higher dimensions, of course, they're exponentially larger, more complex. So we decided to use what is called the tensor network formalism. A tensor network formalism is something like a multi-configurational time-dependent Hartree formalism, okay, but written as a graph structure, except now you can see that it's a MCTDH type of expansion, but now each of these terms are connected in a sequential way. Here I'm presenting a one-dimensional way of writing tensor networks. There are more general ways of writing tensor networks, and these are the internal variables, which are called the entanglement variables, and then these can be propagated simultaneously, and that's exactly what you've done. Okay, so what we do now is to then spawn out each of these one-dimensional blocks on separate ion trap quantum computers, on separate ion trap quantum computers, and you end up with a family of quantum dynamics trajectories. How many of them? As many you have dimensions multiplied by the amount of entanglement you have in the system. So parallelism is a little complicated now. It's not just one trajectory for each dimension, but multiple copies for the extent of entanglement, right? And let's see how that comes about. When you go to higher dimensions, you can see that this is a string of very large dimensional tensors, which are all propagating forward in time, which are all entangled, and they're all giving individual Hamiltonians. Okay, each of these are individual Hamiltonians. These are all one-dimensional Hamiltonians. But how many of them? As many as dimensions, but also as many as entanglement variables right there. So many copies of entangled quantum wave packet dynamics are occurring, all of them on many ion traps simultaneously, right? So this we did on IonQ's 11-qubit quantum system for 2 dimensions. That's what we have implemented. Right now we are working on higher dimensions back on DOE's quantum system, and we have some results already from there. Results are pretty good. But the results I'm going to show you today is from IonQ. The way in which entanglement occurs in this particular formalism is through these internal variables right here that connects these different tensor cores. So what that does is that these Hamiltonians become non-Hermitian. So you're going to do non-Hermitian quantum dynamics. Each of these legs is non-Hermitian. So non-Hermitian quantum dynamics is being done on several of these quantum computers, and the way in which we do this using something called block encoding. So block encoding is the whole matrix is not unitary, but you can convert it into a unitary matrix by doing something called a cosine sine decomposition, where the individual blocks are given analytically. And so then we do that way, and we can get results for such systems with reasonable efficiency. Now, if you did not use tensor networks, then as the number of dimensions grow, okay, this would be the quantum circuit depth, and that's a log scale. So essentially impossible to do. But with tensor networks, as you can see, the log scale, the numbers have come down tremendously. But then there's a price to pay for entanglement, right? Systems with highly entangled states, so alpha, the inner variable here, is 100. So I club together those variables together and call them alpha. And so those variables, if there are 100 dimensions that are entangled, it's much more expensive, right? Much more expensive, but clearly not to the same extent as in the original problem, right? So there is some big advantage here to be had. Of course, when you can do all of this stuff, the question is, can we do this classically, right? Why would you need a quantum computer? It's a very good question. We do not know. This could be an example of what one might call a quantum-inspired classical algorithm, which might push quantum dynamics forward. So because we would never have thought about these things without quantum computing. So such quantum-inspired classical algorithms could also become interesting in the future. So using this, we have of course done the vibrational spectroscopy of a simple two-dimensional system, and these are experimental results. Okay, the circles are all from experiments, and the vertical dashes are theoretical calculations. They match pretty well. The peaks match pretty well from the vibrational spectrum that you get from the experiments. And when we go on and compute the entire vibrational ladder for this system, and the accuracy is of the order of a tenth of a kcal per mole in terms of these energy states. So we can do these things for quantum dynamics. We hope that we can continue doing this in higher dimensions, and probably this would be very good for large dimensional problems. But that time will tell as we go to higher dimensions. Electronic structure. Again, the same problem in electronic structure. Quantum circuit depth explodes exponentially. Cannot really solve any problem with these kind of an architecture. So we want to think about these electronic structure problems and the corresponding quantum circuit depth in a different way, okay, in a way that Krishnan spoke about earlier. So if you introduce a Venn diagram, but now this Venn diagram is in Hilbert space, all right, and so you take this Hilbert space and this Venn diagram partitions the Hilbert space. The Hilbert space now is given by the resolution of identity. That's now the union of all three sets that I've shown out here, but you can write that according to the inclusion-exclusion principle as a set of projection operators which now act on individual sets only. So once you have this set of projection operators, what do we do with it? We go to a graph representation first, because the graph representation now allows us to think about more complicated objects of this kind. So each node is a Hilbert space, each edge is a Hilbert space, each face is a Hilbert space. And so we have a variety of projection operators. The rank of the rank R tells you R equal to 0 is a node here in the graph, R equal to 1 is an edge, and so on and so forth. The alpha rank R object has got a specific projection operator. And then M here is a multiplicity, that's the number of times a certain object occurs in all higher dimensional objects. And so this gives us a new identity, which is equivalent to the identity in the previous slide for inclusion-exclusion principle. And then we say there exists a quantum algorithm, okay, and that quantum algorithm is called U, okay. U is a unitary, right, which acts as a quantum algorithm. And so you apply the identity on U, and you get a family of U alpha R's. So this family of U alpha R's are the individual quantum circuits for the various simplexes that are present in this graph. Okay, the simplexes are various rank R objects that are present in this graph. So each of these are much lower complexity. Using this, we actually recover something that looks like the many-body expansion, but now we replace the energies in the many-body expansion with a difference in energy between a high level of theory and a low level of theory. The high level of theory is computed on a quantum computer. The low level of theory can be done classically, and that difference is, it's a many-body expansion with differences in energy, and we actually recover the energy is pretty good for couple cluster with these algorithms. So the circuits look very different depending upon the kind of systems you had. The previous slide had circuits for H2 molecules, many of them. This is for water clusters, right? So the circuits are now derived based on the systems that we're talking about. And again, the quantum circuit depth, which I told you earlier, which grows exponentially with system size, still grows exponentially with system size, but now in our case, it actually does increase with system size, but you cannot see it on this scale, right? It's pretty flat because this is an exponential scale, and so we have at 128 H2 molecules here. Okay, the complexity has come down by 6 to 8 orders of magnitude. We can also do hydrogen-boron systems. These are protonated water clusters, and here we can get accuracies which are in the sub kcals per mole, and we've gone up to 32 water clusters on a quantum. This is a quantum simulator. This is not a real quantum computer, but this quantum algorithms are run on a quantum simulator. Seeing this idea. We've been able to do machine learning algorithms with this. This is a H13O6 plus solvated Zundel cation, and using, so again the same expression, but these energy expressions, the deltas are obtained from machine learning. Okay, and we get so this is about 0.3 kcals per mole for 30,000 geometries. We can go to even larger systems. This is the protonated 21 mer and the 186 dimension. This is a full potential surface, and again the accuracy is 0.3 kcals per mole. And here we have discovered that there's some close connection between what we're doing and natural language processing. So, with that, I'll conclude my talk. The summary is that we are developing these quantum algorithms for electronic structure as well as quantum dynamics. The basic idea is that we wish to bring down the algorithmic complexity of these quantum systems by several orders of magnitude, and this we do by reducing the quantum circuit depth, both for quantum dynamics as well as for electronic structure, and also use similar methods for machine learning. And as I said, this is a collaborative work which is done with physics faculty and computer science faculty. All of the quantum computing work is done by 2 graduate students. The funding comes from various NSF sources. And there's an advertisement that I want to put in for Indiana University for all those students who are interested in future prospects. Indiana is an excellent place to be at for a variety of reasons. Some of them are political, but we will not talk about that. But the non-political reasons being that at Indiana, we have this collaboration between Indiana University, Purdue, and Notre Dame, which allows us to have this, the first industry university collaborative research consortium. And so our research is funded by 10 companies and the National Science Foundation. And that allows us to work on problems that are interesting to industry. And so with that, I'll conclude my talk. Thank you.
Swayam Prabha, Digital India, Educated India.